The third technology enabler is macromolecular chemistry. This is an area of chemistry that studies all the physical and chemical properties of macromolecules or polymers. Modern macromolecular chemistry includes the development of responsive polymers. With responsive polymers, it is possible to produce fabrics which gives the wearer thermal and mechanical protection. The development of macromolecules like dendrimers and cyclodextrin opened the gateway to produce slow or triggered release systems. They can give excellent protection against chemical and biochemical hazards. Composite fibers is a very important class of fibers. Composite fibers consist of a combination of two or more materials. One material serves as a matrix, which holds everything together, while the other material serves as a reinforcement, in the form of fibers embedded in the matrix. This enables us to make fibers with special properties with respect to their strength and their resistance to chemicals and heat. Composite fibers will be very important materials for future PPE, delivering protection against thermal, chemical, and mechanical hazards. The development of sophisticated polymers has led to the development and production of special membranes that are used in special clothing. The membranes, with one side a hydrophobic fabric and on the other side a hydrophilic fabric, form a sandwich composition that is water repellent at the outside and water vapor controlling at the inner side. Membranes are currently used in outwear clothing, but with application of other specific polymers, it is possible to create systems that gives protection against chemical and biochemical hazards. The fourth technology enabler is formed by microsystems and electronics, and we choose to include here the combination with ICT. With the methodology of micro and nanotechnology and microelectronics, it is possible to produce complete, small-scale mechanical and electronic systems for sensing, controlling, and communication purposes. Combined with embedded software, this results into smart systems that can be incorporated into PPEs. Important for this are the developments in the area of micro-mechanical electro systems. Nanotechnology is also applied to develop a so-called micro-electro-mechanical system, or MEMS. These systems are the result of the integration of mechanical elements, sensors, actuators, and electronics on a common silicon substrata through nano-production technology. With the technology of MEMS, it is possible to integrate in PPE alerting and alarming functions. It is very likely that future PPE will contain miniaturized sensors and actuators protecting the wearer against many more hazards. Conductive polymers are the future building blocks for flexible and wearable electronics that can be integrated in a PPE to ensure that the wearer is continuously connected to his colleagues and the outside world. The schedule shows how these are interconnected. Note that ICT research opens the road for new systems of data handling and processing. It is impossible to imagine life today without our information and communication systems. Information and communication systems are also indispensable for people wearing PPE. Together with the microsystems engineering and the flexible electronics, it will be possible to integrate the information and communication systems like GSM and GPS fully into fabrics, transforming them into so-called wearable electronics. This kind of system ensures the wearer being connected continuously to his colleagues and to the outside world, and being updated continuously about his situation and environment. The fifth technology enabler for new materials is the advanced production technology. Beside the rapid technological developments in the first four enablers, also new high-tech methods have been introduced in the production technology. Important for the production of PPE are robotics, inkjet technology, and the application of plasmas and lasers. With these technologies, it is possible to locally apply, with great precision, specialities or functionalities on fabrics and to modify the surface of the fibers. Robotics is one emerging area that enables producers to make complex products at low cost. With inkjet technology, we can apply functionalities in a very precise and economical way. Plasma and laser technology can alter the properties of surfaces to make them suitable for specific aims, like better coating performance. Conclusion. Our conclusion is that we can now link the technologies to protect from the hazards. These hazards are grouped under a number of main headings, such as chemical or being disconnected. What is striking is that in the future PPE, we will apply all areas of new technology to cope with existing and anticipated hazards. In this overview, we see the current state of developments. Clearly, a lot is already in development and will become available within a short, foreseeable future. And that leads us to the key question for this conference. How is this going to influence future standards? And what needs to be done to cope with this in terms of development? Future solutions will be multidisciplinary and influence each other mutually. They are connected. Therefore, R&D must get access to all these areas. It must take into account the status of the knowledge available. So a lot will be determined by the outcome of current research. But for now, what is even more important is how will we implement this and develop applications, and when. That leads us to the objectives of this conference. 1. What are the consequences of this roadmap? 2. What must be done by our branch to anticipate the consequences of these developments?